Alright, so today we'll be discussing simple harmonic motion. I've already solved some problems for you, but we will go over them. So here we have a simple mass and spring system horizontally. So it doesn't matter if it's vertical or horizontal. And we have a spring constant of 0.2 newtons per meter, and we have a mass of 5 kilograms. This also has a mass of 5 kilograms. This is a simple pendulum, but we'll get into this later. And its maximum displacement is 3 meters. So it's pulled back 3 meters, then let go, and then it oscillates back and forth. So what's the period? Well, it's just 2 pi times the square root of the mass over the spring constant, and this just gives you 31.4 seconds. The frequency is just the inverse of the period, and this is going to give you 0.032 hertz. And your rotational frequency is just 2 pi times the frequency, which is just the same thing as the square root of k over m, which is going to give you 0.2 radians per second. Your amplitude is just the same thing as your maximum displacement, how far it's been pulled back before it's released, which is just 3 meters. Then you have your maximum velocity, which is just the amplitude times your rotational frequency, which is just 0.6 meters per second. And then you have your max acceleration, which is just your amplitude times your rotational frequency squared, a omega squared, and you get 0.12 meters per second squared. And then here are the graphs of the function of position as it relates to time, velocity as it relates to time, and acceleration as it relates to time. And so this starts off at maximum displacement, is released, and then it gets closer and closer to the equilibrium point, and at a fourth of the period, it reaches its equilibrium point. So a fourth of the period, half of the period, 3/4 of the period, 1 period. Okay? And so it's like this. That was my cosine wave sound. Okay? And why is this a cosine wave? Well, because max displacement, equilibrium, max displacement but in the opposite direction, equilibrium, returned back to this original position. And so the formula for this is just 3 cosine 0.2t, because it's just the amplitude times the cosine of the rotational frequency times the time. So a cosine omega t. And then here we have velocity. It's just the derivative of 3 cosine omega of the amplitude times cosine omega t, because that's how position, velocity, and acceleration work. Is just the derivative of that. Okay? And so the derivative of this is just negative a omega sine of omega t. Chain rule, of course. You take the derivative of the inside as well. And so if we apply this, we get negative 0.6 sine 0.2t, which is just the maximum velocity negative, because it starts off at 0, and then it's going to the left, so it's going to be negative, and then it reaches 0 again here, and then it goes back up, but it's positive because it's going to the right. 0.2t, and that's it. And it's the same thing for acceleration, maximum, and it starts off at maximum but negative because it's going to the equilibrium position from the left, and then it stops, and now it's positive because it's accelerating towards the equilibrium position but to the right. And so this is just a negative cosine wave. How can we tell? Because it's just this flipped over. And so this is just negative 0.12 cosine of 0.2t. And then we have the same thing here. And the only difference is that the period is the square root of L over G. And you can take a look at this, these solutions, screenshot it. And this, I believe, is a good way to depict how these two systems work. So a simple pendulum and a simple mass and spring system.